Hello, in this video, we will discuss about equilibrium constant and reaction quotient. First of all, we need to understand what are the reaction at equilibrium. Supposing in any reaction, A and B is reacting to give you C and D, but with the same rate, C and D is again giving you A and B. So in that way, the concentration of reactant and concentration of product becomes constant, does not become equal, but it becomes constant. That means, let's take an example. Supposing in a mall, you are going up using an escalator, but escalator is coming down with the same speed. So though the process is happening, but you will not observe any change. Such type of process is at equilibrium. That means A and B is converting to C and D, but the concentration of C and D is not increasing because C and D is again converting to A and B with the same rate. Supposing you are adding a digit by 1 and at the same time you are subtracting the digit by 1. That means you will not observe any change in the given digit. Such type of reactions are called reaction at equilibrium. Now, we need to understand how to find out the equilibrium constant of any reaction if it is at equilibrium. All right. So first of all, we need to see law of mass action that says the rate of forward reaction. Forward means this reactant converting to the product is directly proportional to active mass of reactant. That you can call the concentration of A and concentration of B, but actually it is not the concentration. This is the concentration that is actively participating in the reaction. So it is called active mass. That is another topic. You will be knowing about that later on. But for now, you need to understand the rate of forward reaction is directly proportional to the concentration of reactants, and in the same way, rate of backward reaction is directly proportional to concentration of product. We'll be writing it as RF and RB. All right. Now, as we are talking about the equilibrium, like we are discussing this at equilibrium. At equilibrium, the rate of forward reaction becomes equal to the rate of backward reaction. That means RF is equals to RB. Let's say RF means like if we remove this proportionality symbol, we'll be introducing a constant. Like this can also be represented as RF is equals to, let's say, K of forward reaction, concentration of A, concentration of B. RB is equals to KB. KB is the constant for the backward reaction, concentration of the products. All right. Now put the value of RF and RB. So we'll be writing KF. So concentration of A, concentration of B is equals to concentration of KB. Now we have calculated the ratio of rate constant for forward reaction and backward reaction. That is obviously a new constant. The ratio of a constant is always a constant. That will be called the equilibrium constant K. All right. Now, supposing in this reaction, like I have not mentioned any coefficient, any stoichiometric coefficient. Supposing we have the coefficient 3 over here, 2 over here, right? So, what is the meaning of 3a? Meaning of 3a is A is written thrice. Okay. So, in the rate law, the rate for the forward reaction, you will be writing concentration of A, concentration of A, concentration of A 3 times. If 3 is multiplied over here, so you will be writing this term 3 times. That means it will become in the power A into A cube. Okay. Same with the B square. So what did you learn here? That means if the stoichiometric coefficients are written in the reaction, then while writing the rate law, we will be writing this in the powers. Okay. So it will become like cube here, square here, then it will become cube here, square here. Okay. Now, using this, let's introduce a reaction and write down the value for the equilibrium constant that particular reaction. Suppose we have a reaction N2 plus 3H2 gives you 2NH3, right? This is at equilibrium. So you need to write the K for this. So what is the formula? You need to take the concentration of product divided by the concentration of reactant. So what is the product? Product is the ammonia. So concentration of ammonia, and this concentration is active mass actually, to the square. The coefficient will go in the square divided by concentration of N2. What is the coefficient of N2? 1. And concentration of H2, the coefficient of 3. Let's take another example. See this reaction, NH4Cl solid giving you ammonia and HCl. The physical states are written gas, gas, solid. Keep remember, while writing the equilibrium constant, the active mass for pure solid and pure liquid is considered as unity, 1. So we'll be writing the product. Product is concentration of NH3, no coefficient, so no powers, that is the 1. And the concentration of HCl, 1 is the coefficient, so 1 is the power, divided by active mass of NH4Cl, but that would be taken as unity. So the finally it will become, unity means 1, we'll take it 1. So finally it will become NH3 and HCl. Alright, so if the pure liquid or pure solid is given, we'll take it as 1. Now this was all about the equilibrium constant. Let's discuss about reaction quotient. To discuss the reaction quotient, supposing I have taken another example, the hypothetical reaction. Now we have written the equilibrium constant K for this reaction. Concentration of C, power to the C. This C is representing the coefficient. It can be any unit, 1, 2, 3, 4, any of the constant digit. Concentration of D to the power D. This can be any of the multiple like 3, 4, 5, whatever. In the same way, A to the power A, B to the power B, and these A, small a and small b are obviously some coefficient that can be a constant 1, 2, 3, 4 and so on. This can be written only if the reaction is at equilibrium. This ratio is representing the equilibrium constant if this reaction is at equilibrium. But if this reaction is not at equilibrium, these ratios will be representing reaction quotient. That the symbol is Q. That means if this reaction is not at equilibrium, at that time you are writing the same ratio, this cannot be called equilibrium constant, rather than it will be called reaction quotient. Alright, now supposing we can have two cases. The first case is the value of this Q, if the reaction I am talking about, if the reaction is not at equilibrium. So this Q value can be either greater than K, or this Q value can be either less than K. If Q value is equal to the K, that means it is the equilibrium case only. If Q value is equal to the K, that means you are discussing the same case at the equilibrium. But if it is not, it is not equal to the K, that means reaction is not at equilibrium. Now, if it is not equal, there are only two cases possible: Q greater than K, Q less than K. Enough, you can write QC also for the terms of concentration, right? Now, if QC is greater than K, what does that mean? That means the value of numerator is obviously higher. In the numerator, you have product. If concentration of product is higher, then obviously reaction will go backward. If the concentration of product is higher, reaction will go backward to minimize that. If the concentration of reaction is higher, the reaction will go in forward direction. Keep remember, product concentration higher, reaction will go backward. Reactant concentration higher, reaction will go forward. So that means if QC is greater, that means product concentration is higher. So reaction will go in backward direction. If QC is less than KC, that means what is higher? The denominator is higher. That means the concentration of reactant is higher. In this way, the reaction is going forward direction. All right. So, and if they are equal, that means you are discussing the case of equilibrium. So in this way, we'll have questions to decide whether the reaction will go in the forward direction or backward direction. In the next video, I'll try to summarize about the La Chatelier principle, another important principle of the chapter. Thank you.